A chemical bond forms when atoms are more stable at a certain distance from each other than they would be if they were closer together or further apart. If we were to make a graph of what this looks like, we would want the x-axis to show distance apart and the energy on the y-axis. A bond will form if there's a minimum on our graph, like a valley, some point where the energy resulting from the atoms' interaction is lower than if they were infinitely far apart. As long as the atom doesn't have enough energy to escape the valley, it stays in the bond. So the depth of that curve tells us how strong the bond is, or how much heat or work it would take to push the atom up the hill and out of the valley. The curves describing the bonds in nonmetal covalent network solids are sharp-sided and very deep. The relatively small number of electrons so close to the nucleus means that it takes a large amount of energy to change the bond length. For an example, think of a diamond. Every carbon atom is very stable in its position, sharing its 4 valence electrons with 4 other carbons, all of them completing each other's shells. Because there are just enough electrons to satisfy the orbital occupancy, electrons aren't able to move easily from atom to atom. And since that is necessary for electrical conduction, diamond is a very poor electrical conductor, or a good electrical insulator. An atom absorbs heat by moving around in space, but carbon atoms in diamond are confined to their energy valley. It takes a lot of heat to let them move much, making diamond very hard, acid and base resistant, and very bad at transmitting heat. Diamond can burn, but only if the crystals are on the nanoscale, and even then they're not very flammable. It's similar with other nonmetal solids, but the depth of the valley can change with the elements or even the arrangement of atoms. Carbon in graphite behaves differently than it does in diamond. In fact, carbon in graphite behaves differently than even a single layer of graphite, which we call graphene, which is different than 2 layers of graphene, or if the layer is rolled into a tube or a ball. Metals are a different story. Metallic solids still share electrons, but because metals can become more stable by losing electrons, they're not closely held between the nuclei. Instead, the covalent electrons are shared equally between all atoms, a quantum effect called delocalization. It's like each electron was spread out into a thin wave that peaks just a little bit around each atom. And remember how we said that every electron in an atomic system has to have a different set of quantum numbers? Well, when we extend that idea to the unimaginably large number of atoms in a metal solid, it means that every electron has to rest at a slightly different energy level. So instead of absorbing and emitting single frequencies of light, metal surfaces absorb and reflect entire bands of light. And that's what makes them so shiny and reflective. Electron delocalization also makes the energy well wider and shallower for metals than for nonmetals. That means they conduct heat more easily and have a lower melting temperature. It also means that they're generally soft and workable. They bend and shape easily. Unlike salt crystals, salts, or ionic lattices, are made of ions that hold their electrons tightly to each atomic nucleus and are only held together by electrostatic attraction. Because they aren't really sharing their electrons, ionic lattices don't conduct electricity very well. Their bonds are weaker than covalent bonds, making them more subject to chemical attack. They'll even dissolve in water. And they'll melt at hundreds instead of thousands of degrees Celsius. And the neat, orderly rows of alternating charges means that salts are typically hard, but also brittle. And finally, we get to solids made up of molecules. Intermolecular forces like hydrogen bonding, dipole-dipole interactions, or London dispersion forces can have enough of an energy benefit to hold molecules together into a solid. Sugar crystals, for example, are made up of sucrose molecules. They'll also dissolve in water, and they'll melt at cooking temperatures. Ice is another example. It's a solid held together by hydrogen bonds, but those bonds are weak enough that they melt at 0 degrees Celsius. Both sugar and water are polar molecules, and their dipole moments help to stabilize them as solids. Nonpolar molecules have a more difficult time. Octane, for example, is a heavier molecule than water, but doesn't solidify until around negative 57 degrees Celsius. It takes a much longer carbon chain for the weak London dispersion forces to hold hydrocarbons into a solid, and even then a few changes in geometry are enough to prevent solidification. This can explain why animal fat, a straight, saturated hydrocarbon, is a solid at room temperature, but vegetable oil, a bent, unsaturated hydrocarbon, is a liquid. So there you have it. Understanding the electronic structure and the bonding inside of materials helps us to understand their properties and their uses. These days, that understanding is being applied by scientists here at RMC and elsewhere to creating new materials tailor-made for advanced functions, and some that even have properties that no one has ever seen before. It's hard to describe the feeling of that kind of discovery, being the first to know something or to hold the entire world supply of a thing in your hands. But that's part of the joy of scientific research.